Thank you to the Young Mathematicians Conference Organizing Committee for giving me the opportunity to present this research. In this presentation, we're going to go over the delta unlinking number of algebraically split links. This is what we researched in the RU that I had the great privilege to participate in, along with some of my friends, Janelle, Gabriel, Noe, and Dr. Bosman. In this presentation, we first outline and understand what a knot and link are, some background in knot theory, and we then define the delta move, the star of the show, and concepts such as the delta unknotting number and delta Gordian distance for knots. We'll see then how, in our research, we generalize these ideas to the delta unlinking number and delta Gordian distance for links. Afterwards, we'll go over a series of methods that we use to fully determine and calculate the delta unlinking number for these links up to 9 crossings. Methods such as the sum of delta unknotting numbers, the canonical unlinking number, the Arf invariant, and the 4 genus. At the end of our research, we tabulated these results. So if we first go into a bit of background in knot theory, let's understand what a knot and a link are. So a knot is simply an embedding of a circle into three-dimensional space, with a link being an embedding of one or more of these circles, possibly knotted and linked together. We consider two of these knots or links equivalent if we can deform one into the other without letting it pass through itself. So if we look at this link diagram right here, if you look at this blue component and this strand that goes on top, notice we can remove this overlapping by simply pulling it up and away from this strand that's passing through, giving us this completely equivalent link diagram to the right. We then say that these two links are ambient isotopic to each other. This prompts the discussion though, what if we allow these knots or links to pass through themselves? This introduces us to the idea of a crossing change. So a crossing change is a local move on a knot diagram, and unsurprisingly, it should be kind of intuitive that this local move, the crossing change, is an unknotting operation. In other words, we can take any knot diagram and unknot it via a finite series of crossing changes. So if we look at this diagram right here of the trefoil, notice that I can perform a crossing change right here, where this strand turns from an undercrossing to an overcrossing. Then I can pull this strand down and untwist, giving me the unknot. This introduces the idea of unknotting number and unlinking number, where the unknotting number is simply the minimum number of crossing changes necessary to transform a knot diagram into the unknot, and the unlinking number being the minimum number of crossing changes necessary to unlink and unknot any link. On the topic of local moves, we can look at another local move, namely the delta move, which is shown in the diagram. So more surprisingly and less intuitively, the delta move is also an unknotting operation, meaning we can take any knot diagram and move it into the unknot via a finite sequence of delta moves. For example, if we look back to the trefoil, we can perform a delta move right here, giving us the corresponding diagram, in which we can then untwist all the ends, giving us the unknot. This introduces the concept of delta unknotting number, which is the minimum number of delta moves necessary to transform a knot K into the unknot. For example, the delta unknotting number of 3,1 of the trefoil is equivalent to 1, and the delta unknotting number of 5,2 is equal to 2. Nakamura, Nakanishi, and Uchida in 1998 determined the delta unknotting number for knots up to 10 crossings, and Okada in 1989 determined the delta Gordian distance for knots up to 6 crossings, where the delta Gordian distance between two knots is the minimum number of delta moves necessary to transform a diagram of one knot into the other. So this is understood for knots and well studied, but let's look at it in the context of links now. Given an example, the Bromian rings, or L6A4, we see that this link is also delta equivalent now to the trivial link, where we can perform a delta move here on the center, which gives us this corresponding diagram, in which we can then free all the components away from each other by simply pulling them away from each other, giving us the trivial link. This prompts us with the question, which links exactly are delta equivalent to the trivial link? To do so, we look at a theorem proven by Murakami and Nakanishi in 1989, which states, given two links with the same number of components, They are delta equivalent if and only if they share the same pairwise linking information. The linking number, or pairwise linking number, measures how many times one component passes through the other. If we look at these two links on the left, we see that although the red component here is knotted and this one isn't, they still pass through the blue component the same number of times. Likewise, the red component and the green component in these two links are not knotted or linked at all, and as a result, their pairwise linking number is equal to 0. We can compare that to these two links, the Borromean rings and the trivial link, in that although the Borromean rings are linked together as a system, if you look at pairs of components, say the red and the green component, they're not linked. If you were to only focus on the red and the green component, you'll see that the green component passes over the red component both times. And as a result, if you were to look at them individually as a pair, you can just pull the green component up and off of the red component, meaning that their pairwise linking number is equal to 0. So we say that links that have the same pairwise linking information as the trivial link are algebraically split links. These are the links that are delta equivalent to the trivial link. Thus, for these links, we can extend our definition as follows. For an algebraically split link, its delta unlinking number is defined to be the minimum number of delta moves necessary to transform it into a trivial link. And for two links with the same number of components and pairwise linking information, the delta Gordian distance can be defined as the minimum number of delta moves necessary to transform one link into the other. In our discussion of delta moves on links, we must also note that there are different types of delta moves that we can perform, namely the self-delta move on one component, in which all three strands of the delta move correspond to one component in the link, a delta move with two components, in which two strands correspond to one component, with the other strand belonging to some other component, and lastly, the delta move with three components, in which each strand in the delta move corresponds to a different component in the link. With this discussion, we can now look at an example and see how we can determine the delta unlinking number for a link. So say we're given a link like L9A10, how can we find and fully determine its delta unlinking number? First, let's start off by knowing that we can manually calculate a pathway that reduces this link into the trivial link in 3 delta moves. But finding a pathway like this only gives us some upper bound. It doesn't allow us to fully determine a value, only what it can be at most. So the name of the game is we must derive and determine new methods for improving lower bounds of these delta unlinking numbers until we can get these bounds to agree, allowing us to fully determine the delta unlinking number. The first of these methods is the sum of delta unknotting numbers. So we proved that given a link with m components, its delta unlinking number is bounded below by the sum of delta unknotting numbers of its components. The idea for this theorem is that only self-delta moves can change the knot type, but it can only change the knot type of a single component at a time. And thus, if we want to completely unknot and unlink, we're going to have to unknot all the components, add up their delta unknotting numbers, but we might also need additional delta moves to fully split the link apart, and thus the result follows. In the case of our example, L9A10, we have that if you add the delta unknotting number of the green component with the delta unknotting number of the blue component, we get a sum of 2, which gives us a lower bound for our link, L9A10, having a delta unlinking number bounded below by 2 and above by 3. But this is still insufficient to fully determine the delta unlinking number. Thus, we move on to the next method, the canonical unlinking number. The idea is we can represent each delta move by simply doing 2 crossing changes. This yields the inequality that the canonical unlinking number is less than or equal to 2 times the delta unlinking number. By dividing by 2 on both sides, we get the theorem that the delta unlinking number of a link is bounded below by half of the canonical unlinking number of that same link. Remember, we have that the delta unlinking number of L9A10 was bounded below by 2 and above by 3. If we apply method 2, we know that, and it is known, that the canonical unlinking number of L9A10 is equal to 3, and thus the delta unlinking number of our link is bounded below by half of this value, or 1.5. But unfortunately, this also does not improve our lower bound, and we'll need another method. This introduces our discussion of the Arf invariant. The Arf invariant is a binary value, 0 or 1, which is defined for knots and can be generalized to proper links, in which our links, algebraically split links, fall as a subfamily of these. Now we prove the following result, which generalized from knots, that given delta equivalent proper links L and L prime, we have that the delta Gordian distance between these two links is congruent to the sum of their Arf invariants mod 2. The idea for this proof is that a delta move changes the Arf invariant by 1. And so if two links have some delta Gordian distance of n, then performing n delta moves to get from one link to the other changes the Arf invariant by plus or minus 1 times, which is congruent to n mod 2. As a corollary of this theorem, if we now set L prime to the trivial link in our theorem, we get that the delta unlinking number of a link is congruent to the Arf invariant of that link mod 2. Finally, using that with this example of L9A10, we have that the Arf invariant of this link is equal to 1, it is known, and as a result, we get that the delta unlinking number of this link is congruent to 1 mod 2. In other words, the Arf invariant allows us to determine the parity of the delta unlinking number of these links. Thus, we can finally determine that if it's congruent to 1 mod 2, it must be odd, and then that means it cannot be 2, and as a result, the delta unlinking number of this link, L9A10, is equal to 3. Again, the whole idea is we discover new methods in order to improve the lower bounds of these delta unlinking numbers after we calculate some upper bound by finding a pathway. Then, if we can keep improving these lower and upper bounds by finding new pathways or by finding new methods, we can finally get these lower and upper bounds to agree, allowing us to fully determine the delta unlinking number. We can look at this in another example, the link L9A40. First, note that we found a delta pathway of length 3, and as a result, we get an upper bound for the delta unlinking number of this link to be 3. If we use method 1, the sum of delta unknotting numbers, note that although this green component may be twisted, it's not necessarily knotted. And as a result, the sum of the delta unknotting numbers for this link is 0, which is not helpful. If we look at our second method, the canonical unlinking number, it is known that the canonical unlinking number of L9A40 is equal to 2. Half of this gives us a lower bound of 1, which doesn't really change anything, also not helpful. If we use method 3, the Arf invariant, we can determine the parity and see that the delta unlinking number of our link has to be odd. In other words, it's either 1 or 3. But yet, with these three methods, it's not enough to fully determine the delta unlinking number for this link, and so we must talk about an additional method. This prompts our discussion of the 4 genus. The idea is, knots and links can be thought of as boundaries of some 4-dimensional surface. Now, for links, we can think of these components as all being the boundary of one surface, or as being boundaries of their own disjoint surfaces. If we look in the latter case, where each component is the boundary of some 4-dimensional surface, we can add up the genera of these surfaces and introduce the notion of the 4 genus, where the 4 genus is the minimum sum of the genera of these disjoint surfaces. An example of this is the Borromean rings having a 4 genus of 1. Now, if we look at the link diagram and then a 2-dimensional representation of its 4-dimensional surface, we can look at them step by step and see what's going on. So first, notice that although this is a slightly different representation of the Borromean rings, it's ambient isotopic. We can introduce a band fusion to this red component, which in 4-dimensional space corresponds to splitting this component into 2 and introducing the saddle right here. By introducing this band fusion, it splits it into 2 components, allowing us to pull the blue component free and out. Now, we can introduce a band fusion yet again to fuse these 2 red components back into 1, which in 4-dimensional space is this saddle point, fusing these 2 components back into 1. And then that allows us to completely pull the red component away and up from the green component, giving us the trivial link. The reason why this is so important is because a delta move can be accomplished by simply fusing the link with a copy of the Borromean rings where you want to perform the delta move. Since the 4 genus of the Borromean rings is 1, we see that each of these delta moves then contributes 1 to the 4 genus. This yields the idea for this theorem where it generalized from knots. Given 2 links with the same number of components, we have that their delta Gordian distance is bounded below by the absolute value of the difference of their four genera. If we let L prime equal the trivial link, as a corollary we have that the delta unlinking number of a link is bounded below by the four genus of that link, which proves to be another useful lower bound for determining the delta unlinking number. Using this new method, if we jump back to our example, remember we had a pathway of length 3 giving us an upper bound of 3, and the R invariant helping us determine its parity. Note, since the R invariant was congruent to 1, we know that the delta unlinking number for this link has to be either 1 or 3. Using the 4 genus, it is known that the 4 genus of this link is equal to 2, and as a result, we can fully determine again that the delta unlinking number for L9A40, this link, is equal to 3. So by using these different methods, we are able to improve lower bounds and agree these lower bounds with a lot of upper bounds that we discovered, allowing us to determine the delta unlinking number for these links, algebraically split links, up to 9 crossings. If we look at an example, say L7A3, note that we found some upper bound, a path of length 3. The canonical unlinking number, method 2, and the sum of delta unlinking numbers, method 1, didn't really help much in improving the lower bound. The R invariant allowed us to determine the parity, being that it's an odd number since it's equal to 1, and the 4 genus allowed us to determine that it has to be greater than 2, greater than or equal to 2, which allows us to fully determine this value to be 3. You'll see though that there were some links, namely L9A14, L9A15, and L9A17, in which we couldn't fully determine the delta unlinking number. Instead, we were only able to break it down into two options, namely 4 or 6, 3 or 5, or 2 or 4 respectively. After all this, we were able to compile this information of delta moves into a tree of delta pathways. The idea being that a delta move changes the link into some other link that's also delta equivalent to the trivial link. So we were able to compile one such pathway for each of these links into a tree as such, and it makes for a cool infographic. A special thank you to the Mathematical Association of America, the National Science Foundation, and Andrews University for sponsoring this 2021 National Research Experience for Undergraduates program. And a thank you for listening.